So today we're looking at section 9.1, lesson 2 about sequences. Our objectives are understand the definition of a monotonic sequence. So what is a monotonic sequence? And of course, that's our vocabulary for today. Objective 2, determine whether a sequence is monotonic by algebraically comparing successive terms. And objective 3, determine whether a sequence is monotonic by using the test for increasing, decreasing functions that you learned in calculus AB. So objectives 2 and 3 are two different ways you can determine whether a sequence is monotonic or not. So here we have the definition of a monotonic sequence. This is from your book on page 600. So what does it mean for a sequence to be monotonic? Let's look at the definition. A sequence, and this is the notation for a sequence, is monotonic if its terms are non-decreasing, meaning the terms are either staying the same or possibly getting larger. That's what we mean by non-decreasing. Or if its terms are non-increasing, which means the terms are staying the same or staying constant or possibly getting smaller. So those are examples. Those are the two different ways in which you can have a monotonic sequence. So we will begin by considering this particular sequence. We saw this yesterday in our activity. So here we have an example of a monotonic sequence. What makes this sequence monotonic? Well, it is non-increasing. It is also non-decreasing. In fact, all of the terms are the same. They're all zero. So it's non-decreasing. The terms are not decreasing. You can also say it's non-increasing. The terms are not increasing. So this is an example of a monotonic sequence. So this is an example of a monotonic sequence. You can see that the terms are non-increasing. In fact, in this particular case, the terms are decreasing. So we have a monotonic sequence here. So here we have a sequence that is not monotonic. The reason why it's not monotonic is because you can see that the terms are alternating between 2 and 4. So we cannot say that the sequence is non-decreasing because as we go from 4 to 2, it is decreasing. But we cannot say that the sequence is non-increasing because as we go from 2 to 4, it is increasing. So it's neither of these. And this is a non-example, or this is an example of a sequence that is not monotonic. So now we want to take a look at objective 2, which is to determine whether a sequence is monotonic by algebraically comparing a successive pair of terms, consecutive terms. So if you take a look at this, we have our sequence b sub n is equal to 2n over 1 plus n. And you may want to begin by thinking about whether it might be non-decreasing or non-increasing. So I would recommend you write out maybe like the first 2 or 3 terms to have an idea of what's going on with it. Okay, is it non-increasing or is it non-decreasing? So when we write out the first 3 terms of this sequence, we get 1, 1 and 1/3, and 1 and 1/2. So we see that the terms are non-decreasing, so we believe that this sequence might be monotonic. But the work that we've done does not prove that it's monotonic. We have to prove that this sequence is monotonic, and we're going to do that by algebraically comparing pairs of consecutive terms. So what does that mean? So based on what we saw with the first 3 terms, we expect that for a particular n, whatever n may be, the next term, b sub n plus 1, will be greater than or equal to b sub n. So we are expecting that we have a non-decreasing sequence. What we like to do is demonstrate that this relationship will be true for any n, so that when you have an arbitrary consecutive pair of terms, whether we're talking about the 4th and the 5th term, or the 13th and the 14th term, or the 20th and the 21st term, whenever you have an arbitrary pair of consecutive terms, we'd like to show that this relationship will hold for all n. So let's go ahead and do that on the next screen. And then after we do this, we would have shown, if we are able to verify this, the truth of this inequality for all n greater than or equal to 1, where n is an integer, if we're able to verify the truth of this inequality, then we would have shown that this particular sequence is monotonic, because we would have shown that it is non-decreasing. So let's do that on the next screen. So we begin by writing b sub n on the left side of the inequality, so that would just be the given rule. And we want to know if that's less than or equal to b sub n plus 1. So you need to write n plus 1 wherever you see n in the given rule. So we're going to write 2 times n plus 1 over 1 plus n plus 1. And basically what you need to do now is work with the two sides of the inequality and simplify the inequality using algebra until you can see an equivalent inequality that you know to be true. So let's go ahead and take a look at how we can do that. So the next step would be to simplify by cleaning up our expressions a little bit. So you can distribute the 2 here in the numerator on the right side to get 2n plus 2. And in the denominator, you can combine like terms. You have 1 plus 1, which will give you 2. So you have n plus 2. And we know that we're considering n that's greater than or equal to 1. So we know that n is greater than or equal to 1 and n is an integer. Therefore, 1 plus n will be positive and n plus 2 will also be positive. And if we multiply both sides of an inequality by a positive number, the direction of the inequality symbol will not change. So our next step is to multiply both sides of this inequality by the least common denominator, which is 1 plus n times n plus 2. So when I ran out of room here, so I had to write it a little bit above. But when I multiply 1 plus n by n plus 2 on the left side, the 1 plus n will cancel with the 1 plus n in the denominator, and I'm left with 2n times n plus 2. Is that less than or equal to? On the right side, when I multiply, n plus 2 will cancel with n plus 2 in the denominator, and I'm left with 2n plus 2 times 1 plus n. So I have gotten rid of the denominators, and now I want to keep working with what I have until I can simplify it so that I get a series of equivalent inequalities until I get to one where I can see and know for sure that what I have is in fact true. So the next step is to go ahead and distribute the 2n on the left side, and that will give me I will come to the to the right half of the screen now. And when I do that, I get 2n squared plus 4n. Is that less than or equal to? And on the right side, I would have to use FOIL to multiply. So 2n times 1 would be 2n. And then I have 2n times n would be 2n squared. So plus 2n squared. And then I have 2 times 1 would be 2. And then I have 2 times n would be 2n. So what you can see with this inequality is that I can subtract 2n squared from both sides of the inequality. And that would give me 4n is less than or equal to 2n plus 2 plus 2n. And on the right side of the inequality, I have 2n and 2n. I can combine those like terms, and I have 4n. Is that less than or equal to 4n plus 2? And the next step is I can subtract 4n from both sides of the inequality. And when I do that, I get 0 is less than or equal to 2, and that I know to be true. 0 is less than or equal to 2, and the idea is this. All of these inequalities that we're looking at from the very first one that we started with to this one are equivalent because we've done the same thing to both sides of each inequality to get equivalent inequalities. So because they're all equivalent, if this one is true, this one must also be true. The very first one must also be true, proving that our sequence is in fact non-decreasing, and therefore by definition it is a monotonic sequence, because this behavior of the sequence being non-decreasing is true for all terms of the sequence from the first term going on to infinity. So we just looked at an example for objective 2, determining whether a sequence is monotonic by algebraically comparing successive terms. There is an alternative way you can do the same work, determining whether a sequence is monotonic by using the test for increasing and decreasing functions that we learned about in Calculus AB. So we will begin by reviewing that test, and then we will apply that test to do a problem in which we'd like to determine whether the given sequence is monotonic or not. In Calculus AB, you learned about the test for increasing and decreasing functions. Let f be a function that is continuous on the closed interval from a to b and differentiable on the open interval from a to b. If the derivative is positive for all x in the interval from a to b, then f is increasing on the interval from a to b. If the derivative is negative for all x in the interval from a to b, then f is decreasing on the interval from a to b. And if the derivative is equal to 0 for all x in the interval from a to b, then f is constant on the interval from a to b. And the easiest way for you to remember this is by looking at the function f of x is equal to x squared. So to determine the intervals on which f of x is equal to x squared is increasing or decreasing, we may use the test for increasing and decreasing functions. And to do that, we need to look at the first derivative. So the first derivative is going to be 2x, and we want to know what are the intervals on which the first derivative is positive and what are the intervals on which the first derivative is negative. So begin by setting the first derivative equal to 0. So you get x is equal to 0. That's called a critical number of the function. So that's going to divide the real number line into two intervals, one from 0 to infinity and one from negative infinity to 0. And you're going to check for the sign of the derivative. So you're going to check for the sign of f prime. So you can choose a test value from each interval. For example, I can choose x is equal to 2 from 0 to infinity. I can choose x is equal to negative 2 from negative infinity to 0. And check for the sign of the derivative. So 2 times 2 is 4, so that's positive. And 2 times negative 2 is negative 4, so that's negative. So on this interval from 0 to infinity, the derivative is positive, and you can see from the graph of the function f of x is equal to x squared that, in fact, on the interval from 0 to infinity, you can see that the function is increasing. And that is consistent with what this theorem is telling us. And you can also see that on the interval from negative infinity to 0, because the derivative is negative, you can see that the function is decreasing. And you can see that on the graph. The graph is falling from left to right. And that is consistent with what this theorem is telling us. So we're going to use this to help us determine whether a given sequence is monotonic or not by looking at the behavior of the corresponding real-valued function. And we're going to see if the corresponding real-valued function is increasing or decreasing on the interval from 1 to infinity. So let's look at an example for that. So here we are taking a look at number 84, and the instructions are determine whether the sequence with the given nth term is monotonic. And we're going to do that by considering the corresponding real-valued function. Now, of course, for the sequence, n is greater than or equal to 1, and n is an element of the set of integers. In other words, n is an integer greater than or equal to 1. So we can look at the corresponding real valued function, which would be f of x, and it would have the same rule, so it would be 3x over x plus 2. And the domain of the real valued function is all real numbers except negative 2, because negative 2 would cause division by 0. If we can show that the corresponding real valued function is monotonic, then the sequence must also be monotonic. So how do we show what's going on with the corresponding real valued function? We can use the test for increasing and decreasing functions to determine the behavior of the real valued function. But of course, to do that, we need to begin by finding the derivative of the corresponding real valued function. So what you see is that the corresponding real valued function is a quotient. So to find the derivative of it, you must use the quotient rule. We apply the quotient rule to find the derivative of f of x. The denominator times the derivative of the numerator will give us, the derivative of the numerator is 3, so we will have 3 times x plus 2, minus the numerator times the derivative of the denominator. The derivative of the denominator is 1, so we just have minus 3x, all over x plus 2 squared. And then you can distribute the 3 here, so you get 3x plus 6. So we're going to have 3x plus 6 minus 3x over x plus 2 squared. So 3x minus 3x is 0. So the derivative is 6 over x plus 2 squared. So now that we have found the derivative of the function, we can use the test for increasing and decreasing functions to determine whether the function f of x is increasing or decreasing, especially on the interval from 1 to infinity. Because for the sequence, we're only concerned with n greater than or equal to 1, where n is an integer. So we really need to know what's going on with this function for x that is greater than 1. So we're really just interested in what's going on with the function's behavior for x values that are greater than 1, because for the sequence, we only need to know what's going on for n greater than or equal to 1, where n is an integer. So what's going on on this interval for the function f of x? Well, we can look at the derivative, and when you look at the derivative, you can analyze what the sign of the derivative has to be. The numerator is always a constant. It is always a positive 6. So the denominator, look at the denominator. Obviously, x cannot be negative 2, but it doesn't matter for us because we're only concerned with what happens for x greater than or equal to 1. So when you square any number, you get a positive number. So the denominator will always be positive because no matter what x plus 2 is, you're going to square it. So you'll always get a positive number in the denominator. And of course, the numerator is always 6, which is positive. So you will have a positive number divided by a positive number for any x greater than or equal to 1. So we know that the derivative of the function will be greater than 0 for any x greater than, or for x that's greater than or equal to 1. And using the theorem from calculus AB, if the derivative is positive for all x in an interval, the function is increasing on that interval. So we may conclude by using what we learned in calculus AB, that the function f of x, it has to be increasing for all x greater than or equal to 1. And because the sequence has the same rule as the function, if the rule for the function is telling us that the function is increasing, the sequence must also be increasing and therefore monotonic. So you may conclude the problem by just writing these two statements here. And you know that because the corresponding real valued function is increasing on the interval from 1 to infinity, the sequence must be monotonic because it is non-decreasing. And of course, just to reiterate, how do we know that the function f is increasing on the interval from 1 to infinity? Because of the test for increasing and decreasing functions, we found that its derivative was positive on the interval from 1 to infinity. This particular problem, number 84, could also have been done the way we did our first example, where you algebraically compare arbitrary pairs of consecutive terms. It could also be done that way. You can refer to our first example for how to do it that way. So we just looked at an example for objective 3, determining whether a sequence is monotonic by using the test for increasing, decreasing functions on the corresponding real valued function. That particular problem that we ended with could also have been done the way we did the first example, where you determine whether a sequence is monotonic by algebraically comparing successive terms. Vocabulary for today: what is a monotonic sequence? And again, we begin with looking at the definition of a monotonic sequence.